Okay, good afternoon. Can everybody hear me?
Yep.
Super, thank you. Yes, I will post the lecture notes at the end of lecture in response to the chat. Okay, so today basically I want to start with a new topic in 824, and it's sort of the last topic that we'll be discussing. And the topic is really decentralized systems. And these are typically, the decentralized really refers to the fact that there's no single authority that is in control of the system. And a lot of the systems that we've seen so far, all the machines and servers sort of cooperate and are under the control of a single institution or any single authority. And the systems that were, and a lot of you ask questions about like, oh, how would it work if there's no central point of trust? And so from now on, the three systems or the three papers that we're going to be discussing all sit in this form of decentralized systems. And decentralized systems are harder to build than the sort of single trust systems because you have to account for Byzantine failures or Byzantine participants. And these are participants that sometimes follow the protocol and sometimes they don't follow the protocol. So really, if you think about it, they're basically adversaries, and they may try to abuse or trick other participants in the systems, for their own goods, but not maybe for others. And so that makes actually system design, or these distributed system designs, much more challenging and much more difficult to reason about. Because like in the last 18 whatever lectures, mostly what we talked about when we designed protocol or we thought about draft, we just assume that actually every participant in the protocol follows the rules. And in a Byzantine, with Byzantine participants, that is not the case anymore. The participant can cook up new messages, send messages out of order, trick other participants. And so the thinking about those kind of protocols is much more difficult because we have to consider like what the adversary could do to sort of make our life, to break basically the properties of the protocols that we're shooting for. So this tends to be make the problem much harder. And really, what this sort of topic is it sits on the intersection of distributed systems and security. And as we'll see in the next this paper and the next three papers, for cryptography or security ideas like signing and hashing and are going to play a crucial role to actually make forward progress. And in fact, the paper actually that we're reading for today is also a paper that we use in 6858. If you're taking maybe 658 last spring, we talked about this paper too, although then mostly from the perspective of security. And today I'm going to mostly focus it on the perspective of distributed systems. The SUNDR itself, a lot of people asked, a lot of you ask, is SUNDR being used? And as far as I know, there's actually no systems that actually implement SUNDR directly or directly based on SUNDR, other than Lab 4 in 6858. In Lab 4, if you do the Lab 4, the default project, which is Lab 4 in 858, then you actually implement SUNDR. Now, the reason, and so you might wonder why we're studying this paper at all. The reason we're studying it because it actually proposes a number of very powerful techniques or powerful ideas. And so particularly the signed log, even though it is a sort of a strawman design or a conceptual design, is incredibly powerful. And you see back that same idea appear in lots of other decentralized systems, ranging from systems like Git to systems like Bitcoin or any other sort of cryptographic ledger, which we're going to be talking about Monday or next Tuesday. I know one system that actually is sort of directly influenced by SUNDR, which is a system called Keybase. And Keybase uses SUNDR techniques and many more. If you're not familiar with Keybase, it actually was recently acquired by Zoom, which you're presumably all familiar with. Okay, so that's sort of for the quick intro to this paper. Before I'll dive into more of the setting, any sort of questions before diving a little bit deeper in the paper? Okay, so let's talk a little bit about the setting of this paper, or the motivation of this paper. So the setting that the author sort of set forward is a network file system. And you can think about this a little bit in the style of an earlier paper that we've read, Francipani, where the topic also was to implement a consistent network file system. And so we have a file server. We have clients that interact with the file server. So somebody might actually create a file, F, and maybe read F on another client. And the setting that we're in is that basically the file server, as opposed to in the Francipani, the file server actually can be Byzantine. And Byzantine really is an extremely powerful threat model, where gives the attacker an incredible amount of power. So in Byzantine, the server might send different RPCs back, cook up its own RPCs, take over the machine, bribe the administrator, and everything is basically, the way to think about it is that the adversary gets complete control of the file server. And so this covers sort of a wide range of sort of more common attacks, or like typical attacks that you might see in real systems, or real attacks. One, bugs in software. So if there's a bug in the software, then the adversary can exploit that bug, maybe to obtain privileges, and the Byzantine model completely encompasses that. Or the system administrator might have a weak password that the attacker compromises, and then takes control over the system. That's also covered by Byzantine. Physical break-in. Maybe the attacker arranges, gets access, to the physical machine, and can therefore control the physical parts of the machine. Again, that's all covered by this, Byzantine threat model. Or even, maybe, the attacker bribes an operator, or colludes, with a malicious client. That is also covered by this model. So this is a threat model that is very, very gives a lot of power to the adversary, and covers a lot of sort of standard attacks. And the first thing sort of to observe, a game that SUNDR plays, is that instead of actually sort of maintaining the whole file system on the file server is as simple as possible. And in fact, the file server is very much like, almost like Pedal. It's almost like a block device with a little bit more. So the sort of central place where all the blocks are stored, but the clients really implement the file system. So it's not really that the client sends a create for a file. It actually sends blocks and reads blocks from the block server, and basically constructs, from the blocks that reads and write, its own view of the file system and serves, file system operations basically straight on the client. And so here really we have, create, F, read F, etc. So very, very similar to the Frangipani, except, the big difference in Frangipani is that Petal and all the clients were completely trusted. And in this setting, the clients are not trusted, and the file servers can be also is also not trusted. Okay. Okay, so the paper focuses on a particular set of security properties, and the focus is really on what is called integrity properties. And in contrast to confidentiality. So confidentiality is about protecting data so that nobody else can read it. Integrity is just ensuring that the system structure is correct, and the modifications, illegal modifications to the data are being detected. And whether the data is public or not public, that's sort of besides the point here. And to make it a little bit more concrete, what they're sort of the thing that they have in their minds is we have a set of, we have developers. We have dev 1, dev 2. They may share, some machine that contains the source code repository of some, source some project. The developers, are collaborating on that project, and sort of think about this as the example that the paper mentions is in the paper. Maybe this is the development machines and the server for Debian Linux, and what they want to again defend against is trapdoor, trapdoor in the software. So an attacker, takes over control, breaks into the machine that contains the source repo, modifies the software unnoticed, and then at some point that software gets deployed. For example, Debian Linux gets deployed to lots of machines, and now the attacker has control over those machines because it can exploit the trapdoor. The paper talks about this attack, this particular instance of Debian Linux in 2003, where attacker was able to compromise the development server or cluster, and recovering from these kinds of attacks is very painful. In fact, in 2003, they report that the Debian Linux sort of froze development for a couple of days while they were trying to sort out which parts of their source repo were still correct and which parts were actually modified by the attacker. And these attacks happen sort of periodically. I think last year, Ubuntu had a similar type of problem in I think in 2018 or 2019. I can't remember exactly. And it was a similar case where one of the core development servers was broken into, and they had to sort of sort out see which software, which files got affected by that break-in. Okay, so that's sort of the setting of the paper, and I'm going to make it a little bit more concrete, and a little bit of a toy example to help us, go through the techniques that this paper actually uses. So the example that I'm going to use is partially inspired by 6858 is, let's say, we have a file system. There's a, you're doing and the file system contains, the source code for this application that we use in 858 called Zubar. And Zubar is a sort of a virtual bank type application where users of the system, registered users of the systems can transfer Zubars to each other. And so it has a file called auth.py, that does authentication, and it has a file that basically implements sort of the bank. It's called bank.py, and so now let's consider the case where we have a set of developers, A, B, and C, and they decide that they want to sort of increase the usability of SUNDR and actually deploy it for real. And to make it real, basically, they decide to divide the work as follows. A is going to modify off.py to support MIT certificates or MIT certs, Kerber's ticket, basically, or certificates. And with the idea that what they're going to do is the off.py is going to be modified so that only legit MIT community members actually can log into the file server or into SUNDR, and so that we actually know who it actually really is that is associated with that particular MIT certificate. And then to make it a little bit more useful, B is going to actually modify the bank PY to actually link it to cache tag or tech cache. And so with the idea that basically we can actually use the SUNDR system. Of course, you should never do that, but like we can use the SUNDR system to actually transfer money, real money instead of SUNDRs, between users that are registered with this service. Now, this sounds, of course, like a crazy idea, and you should not really do it, but it's not completely ridiculous, because the off.py really checks who it actually is based on the MIT certificate. And so maybe it's not unreasonable that we could connect bank to PY to actually tech cache. And then basically C in our scenarios is going to be the person that's actually going to deploy the software. And so it's going to find the machine, takes the software, installs it there, and runs it, and opens it up to the MIT community. Now, in the case, let's consider what could happen, what could go wrong if actually the file server was compromised, and so was visited. Well, the obvious problem, there's a couple of obvious problems, bad outcomes possible. So let's consider them. Bad outcome one, which is the one that we've sort of been talking about also in the previous examples, is basically the adversary gives arbitrary code to C. So adversary provides own code to C. And that's sort of or maybe the adversary is slightly subtle about it or clever about it, whatever. Makes it a little bit hard to spot that actually modified off.py, for example, to delete the MIT certificates. But there's basically, there's really no way for C to check that actually it got the software that A and B produced, and without any modifications from the adversary. So that's sort of the obvious problem. We're going to talk a lot about it. Then there's sort of a second sort of bad outcome, which is maybe a little more subtle, which is that the adversary provides the changes, to bandwidth PY without the changes to off.py. And so at this point, this is pretty problematic, right? Because bank PY is linked to tech cache now, but we actually don't have appropriate authentication of the users anymore. In fact, anybody that actually creates a SUNDR account can now actually interact with tech cache. And so, clearly very, very undesirable and harder to spot, correct? Because basically the adversary actually doesn't really modify any software. I just selectively, presents and takes pieces of it and presents that to C, who then actually goes off and deploys it. And so it's really, of course, the attacks, the paper considers it, of course, attack number 1, 2, but a lot of some of the subtle issues actually are brought out by this sort of second case that we'll be talking about. Any questions so far? About the setting and about the motivation, and before I'm going to try to discuss solutions.
Sorry, the problem with the second case is that the user, that the authentication does not authenticate.
Yeah, it doesn't use the MIT certificates anymore. And so we don't really know actually who logs in.
Thank you.
What about the case where A or like B won't see A's like the fork? Is that
Well, we'll come back to
encompassed
that
in
later.
two?
To that. Let's assume for a second that A and B actually,
Okay.
have talked to each other and divided up the work, so they know that they're supposed to be doing this together.
All right.
I mean, they form a team. They're in close collaboration and contact, and they've divided up the work, and so they know, B tells A when he's done, B tells A when he's done, and then they tell C, go ahead, we're all done. Okay. Okay, so let's start with considering a simple design that is too simple, meaning it doesn't work. But it gives us some, starting points for a more sophisticated design that, hopefully might work. And so the simple plan is that A and B or any, all the files are going to be signed with the person who modified it. So when like A modifies, auth.py, A actually produces a signature and that signed with the public key. Signature signed with the public key of A, and that signature covers the data of the file. And so when C downloads the auth.py, it checks the signature. And if the signature checks out, then C knows that actually this file was produced. This file was indeed produced by A, and might all believe that things are good. And that's the basic plan. And we'll talk a little bit about where the keys are coming from. Although the issue of sort of public key distribution is really an 858 topic, so I'm not going to talk too much about it. But just assume for now that every user has a key, a private key pair. And the private keys are kept secret, and the public keys are public, and every user knows whose public key belongs to who. So now let's consider some attacks and see which ones sort of fail and which ones work. So of course the obvious attack was number one that we talked about on the previous slide, which S modifies files. And that is not a little bit, that's not directly S modifies auth.py. That's not really going to be possible anymore because when C downloads the file and the signature and checks it, and it will see that the signature doesn't check because the data that actually was signed is different than the data that actually the server produced. And so it's not really possible for the server really to modify auth.py without actually being attacked or without being detected. So this is we're sort of in good shape here on this attack, and that's sort of the core attack, right? But there's a lot of other things that S still could do, and so let's consider some of the other things. S could actually, in the way I described, S could send another file and pretend to be auth.py. Because the signature doesn't really say which actually file the data belongs to, and so S could just produce some other file and say like, oh yeah, see, this is actually auth.py. You could believe me, and here's the the signed, here's the signature that was of course produced by S. So of course this could be fixed. Maybe the signature should not only include the data, but it also probably should include the file name. So maybe not too bad, and something that could be addressed. A third, yet another possibility is for S to basically send the contents of old files or old content, and maybe some new. And that's a little bit more difficult now for us to handle, correct, in this too simple plan, because there's no way, basically the files are individually authenticated, but not together. It's not that C gets sort of a consistent picture of the file system. It just gets like signed files, and how those signed files relate to each other in terms of their histories is completely not covered in this too simple design. This is exactly, of course, the issue that this more subtle attack that now could just completely work out, correct? Because S could send the old version of off.py, it will completely check out, and then send the new version of the bank.py, which actually talks to this link to tech cache. And now we're exactly back in the worrisome case where we have an old version of off.py, or not the changes to off.py, not the certificate changes to off.py, and the new version that actually is linked to tech cache. And so this is not so good. And the simple plan that we have here just doesn't deal with this. There's a similar another version of this that where, of course, S can also just claim that the file doesn't exist. And C doesn't really have any way of checking whether that actually is true or not, because again, it doesn't have a global picture where it's a consistent view of the file system. It only knows about signatures for each file. And so you can see that there's this simple design, maybe a good starting point, but we need something more complete. Particularly, we need something that really ties all the file systems, all the files together, that ties the directories together, the content of the directories together. And we have to be able to decide in some way, what is the latest version of the file system. And so that C can't be tricked into, in this sort of problematic case where one file is installed and the other file is not installed. And so that's really what the SUNDR paper tries to address. And the big idea in the paper, and it just turns out to be just a big idea in general, and it's a conceptual idea, even though the paper actually doesn't really implement this big idea directly, it implements it in a more indirect way. It is an incredibly powerful idea. So the big idea is to have a signed log of operations. And of course, you're well familiar with logs of operations, and you can, and this is basically a sort of a beefed up version of it, where there are signatures on the log entries that both cover the entry as well as preceding entries. This turns out to be, as you've seen in all the previous distributed systems and failure recovery protocols that we talked about, the log is actually a very powerful idea to think about like the correctness of the system, and in the same way that idea is sort of carried forward here in this Byzantine context. And so like let me draw a simple log. So it captures what's in the paper. So the log, whatever, has some entries, and let's say we're covering the operation that we are talking about. So there's a modification, mod off.py by A and assigned by A. There's a mod, if everything goes well, there's a mod of the bank.py signed by B. And as we'll talk about in a second, it turns out that not only are the modifications in the log, but also the fetch, so the read operations. So fetch of the log, signed by C, fetch of off.py, and the fetch of bank.py signed by C. And we'll talk about those operations of the fetch operation a little bit. First, I want to talk about the preceding operations first, the modifications. So first of all, what is important to realize is that the signature that is in the record not only covers the current record, but it also covers all the records before it. Let me stop for a second here because I'm not 100% sure if actually, can everybody still hear me? Yes.
Yeah.
Yes.
Okay, good. Okay, like my iPad logged out of the Zoom session. I almost logged in twice, and my iPad logged out. So I just want to make sure that I'm still talking to you and you can hear me. And so that is the case. Okay, so let's just proceed. So what I was
I think we lost Franz.
Can people hear me now? Does anybody hear me?
Yeah.
Yes. we can hear
Oh,
you.
okay, good, good. Okay. I don't know if anything weird happened on your end, but on my end, I got logged out of Zoom and logged back in. Maybe there's a Byzantine server at work. Okay, let me hold on 1 second and get myself in. And let me see, is the video off? Okay, camera. Okay, let me know if I'm good.
Yep.
Okay, good. Well,
No screen sharing yet, but yeah.
okay. Oh, I'm hope this works out better. Okay. So I was at this important point where the signature does not cover the log entry itself, but also covers all the preceding log entries. And so when A adds this modification to off PY to the log, it signs the log record itself plus the preceding log records. And you can think about this, that the preceding log is maybe represented by the content of the preceding log is a cryptographic hash, and in the record basically of the modification to off.py, the cryptographic hash of the preceding part of the log is included and covered by the signature.
So just to be clear, we still can't see the screen.
I can't see the screen. Okay, good, good, good. The screen hasn't changed yet, but let me see if I can do something about that. And, oh yeah, I guess, my Zoom still thinks it is actually sharing the screen, but it doesn't look like it actually is. How about this?
Yep, I can see now.
Okay, thank you. Okay, so I didn't change anything yet, other than I think I was going to draw the next arrow, which basically when B signs, it actually covers all the preceding entries too. And this is sort of good, correct? Because when the client, C actually receives, or actually sees the log entry for B, then it's impossible for the server to drop, the log entry of A, because that will be detected when C actually detects a signature on the log entry of B. So we already made sort of a big step forward in the sense that it's much harder for the server now to selectively drop log entries. So then we're in pretty good shape. The server cannot drop A. And keep these modifications. So that's actually a big step forward. And so let's look a little bit more in detail how this actually is going to play out. So we're the client C, and we're fetching the log to basically roll out the distribution of the software or to install it on a particular machine. The first thing the client does, it actually checks all the signatures. And always the question, of course, is like when you want to check the signature of the log entry, which public key do you use? Because you want to make sure that you're not being tricked in accepting a signature of a modification by A, but it turns out that actually A was not the person actually who signed it. And it turns out that basically to figure out like which key to use to actually verify the signature, the key you use is the owner of the file. So the public key needs to correspond to the owner of the file. And ignoring groups for now, basically only the owner of the file is allowed to modify a file. So for this, for slightly simplified, we can think about it that auth.py is owned by A, and the ID of the file is basically the public key of A. And so we know which public key to use, and can verify the signature with it. And so if somebody else makes a modification that pretends to be A, that actually is not going to check out. So it's really only A that can actually make the modifications, and similar for B. So that's part of the, one thing that's actually clever about SUNDR, which I'm not really going to be talking about. In some sense, the file system is actually doubling both as a file system and as a public key infrastructure, distribution infrastructure. And so it is actually possible to use SUNDR basically to reliably determine which user has which public key. But I'm not really going to talk about this. I really want to focus on the consistency aspects and the more distributed systems aspects. The second thing that the client does is check its own last entry. And this is to protect the client from actually being rolled back by the server in time. So the server can't actually, if the client checks always his last entry, if his last entry is in the log still, then the only way forward for the attacker is to actually roll the file system forward. It can't roll it backwards. So C will check whether if any of its previous operations are in it, and confirm that they're still in it. Actually, its last entry is still in it.
Just a question here.
Yeah.
This only, I think this attack from the server to roll back would only work if no other client wrote to the log after this client's last entry, right? Because otherwise checking signatures would figure that out.
Yeah, although let's talk about it in a second. Maybe, yeah, I mean, you can always play a fork attack, right? So you can always split, the view of the file system into multiple views, but you can at least not roll back the client. Once the client saw a particular file system, you can't go backwards in time. Now, the server can present different file systems in the future, but you can't roll back. Third part, the third part, what the client does is construct the file system. So after it knows that actually it's not a past version of the file system, it basically applies all the modifications and basically builds a file system tree, on the client, and then performs whatever operation it wants to perform. So let's say in the case of C, what it will do is, it will read, auth.py and append an entry to the log. And cite it. So in the case when it reads auth.py, it will produce basically a signature, an entry for this log entry. And basically then the final step in this protocol is it uploads the log to the file server. And clearly this protocol is completely impractical, and really what it is sort of more a conceptual protocol to help us understand why actually we might even be successful in achieving security in the context of a Byzantine server. Because it would be ridiculous, correct, to download the log for every operation, and the log contains the history of all the operations ever happened to the file system. In step 3, the client actually constructs a file system at all the operations ever performed since the beginning of time. And then finally, in step 5, it uploads the whole log back to the server. That seems completely ridiculous, and it is ridiculous in terms of performance, but it will help us understand, when we sort of look at the implementation of a scheme, where it actually has the same set of properties that this sort of conceptual design has. And we'll see later, for example, in the case of Bitcoin, that it literally does actually have a log, since the beginning of time with all operations in it. And so maybe it was a crazy idea, maybe in the context of 2004, but people actually do have these sort of signed logs and really maintain them. And so in that sense, it's not only a big conceptual idea, actually people do it in practice. Any questions so far? Okay, so the one thing that you're probably wondering about, and that was proposed as a question for the reading today, is what is up with these fetches? Why are the fetches in the log 2? Because you might think, well, the only thing that we really care about, like if we think about the way we care about is that only the modifications have to be in the log, because that actually are the things that actually modify the file system. Reads don't really modify this file system, so what's the problem? And so I think I want to do a quick breakout here, and sort of you can brainstorm with each other about what you thought the answer to this particular question was, and hopefully maybe sort of this initial coverage of like SUNDR, maybe has now improved your understanding, and you can sort of figure out like what the answer is, or talk about something else. So I would like to take a maybe do a 5-minute breakout room. Okay, just double checking, everybody back?
Looks like it.
Good, good. Thank you. Okay, so what, I guess let's start with the homework questions. With the homework question, why are the fetches in the log? Anybody?
If you have a read-only server, if there are no fetches, the file system can give it anything.
Can it?
It can give it because there are no fetches in the log. That would mean that the read-only servers would not be doing a lot of the checks that we talked about before. So the go back in time, for example, might maybe not work because it did not put anything in the log because it only fetches.
Yeah. Okay, good. Okay, so I think you're totally on the right track. I was like trying to make it a little bit more precise or more concrete. I think it is correct. So let's assume this is the log looks like, and the C fetches are not in it. And let's so this is the log before actually C downloads the log. And so let's say we're C fetches off the py, right? This is the file that was modified by A. And basically what the server does, the server, instead of actually providing both the modifications A and B, because it has it, right? Which A and B were done with its modifications, it sends the C basically prefix. Since the prefix, that excludes the modifications to A and B. So without mods A and B, right? And so C, fetches this file, or fetches the log. So basically, it's this part of the log. Here's the prefix. The C checks, the signatures, checks whether its preceding operations are in it, and they're all there because C hasn't done any other operation yet. And so basically, it will accept the log, and the log as it is, or the prefix as it is, and basically returns, off the PY to whatever application that is copying the software into the machine that actually is going to run the installed software. So then C fetches bank.py. And this time around, the server sends the whole log. And the C looks at these entries, it's a valid log. And its own operations are presumably in the prefix. Since we didn't care about fetches, it's of course not in the log. And so everything looks good. These are valid modifications. Nothing has been changed. And so C will without the fetches in the log, C will actually accept this log and basically build a file system that has that includes the modifications to A and B and returns the result to the application for bank.py. So that it can install it on the machine that actually is going to run the service. And as you can see, now we're sort of in a bad situation, correct? Because we took the old version of off.py and the new version of bank.py. And the one way you can think about this is that, from C's perspective, what really seemed to be have happened is that while it was reading off.py, there were concurrent modifications to A and B, and it just happened basically at the same time, or at least the server is pretending it happened at the same time, and so so it gets confused, or it can't detect that in fact these applications did happen before in time. And so this is the problem that basically putting the fetches in the log solves. And it's like, let's make that actually just also concrete. And so see why actually this problem is solved in that case.
Professor, I had a question.
Yep.
So I'm having a little trouble understanding what the the interface for fetch and modify is like. What I thought you fetched pretty much like the whole tree and had to rebuild the whole file system. Like basic example. But in the slide before, you're fetching like specific files.
The server is the one that returns the log, correct?
Right.
And so the server can decide, what entries to include.
Yeah.
And we're already seeing that it can't really delete anything out of the middle of the log, right? That's not really possible. But
Right.
it can always send a prefix of the log because the prefix is always consistent with itself.
Yeah.
And so in this first case, correct, it sent the prefix. And in the second case, it sent the whole log.
Yeah.
And so the server can decide to do that, right? But there's like nothing that the client can, or at least like so far, we discussed, there's nothing that how the client could detect that it didn't get like the whole log.
Right. My question is more towards like what the interface is for clients to use, like fetch and modify, like because I thought initially okay, like fetch is like the whole file system.
No. Fetch is a single file.
Okay.
And so basically what a fetch does is it gets the log, like modifications and fetch. Okay, so modifications are all the operations that modify a file. And like if you go back to a slide a little bit earlier, in the modification record, it says explicitly which file is being modified. And what's being signed. And similarly in the fetch, actually it says which file actually this client saw.
Okay. And then so for a fetch, like a client goes through the log but only looks at.
Yeah, the final thing it does is actually read the file that it actually is looking for.
Okay, but does it check every single entry in the log anyways for the signature or
Yeah. Okay, the first step is always check the whole log. Go for and make sure that your last operations in it, whether it's a fetch or a modify. Although in this broken scheme, we drop the fetches. It applies it checks all the signatures, and then it builds up the file system by replaying the log from the beginning of time and get a file system, and then it does its operation. And so in this case, the operation is actually fetched off.py is basically reading it.
Okay.
The reason, basically we talk about fetch and modify is because all operations are basically following one or two camps. Either it's a fetch or it is a modification operation, like writing a file, creating a file. Those are all modification operations. The fetch operations are reading a file, maybe ls in directory, stat a file, that kind of thing.
Okay, and then the modify is also like a modify doesn't fetch. Also fetches the log, but then and builds the file system.
Yeah.
But
So
then,
maybe the fetches here, I'm using fetch, I guess, in two ways. One, to describe read-only operations, and actually to get, to obtain or receive the log from the server.
Okay, but then modify is also one single file.
Yes. Yeah. For every modification in the file system, you're going to have a log entry.
Okay. Thanks.
Sorry, I also have a question. I don't really understand why this scenario is a problem, because as you said, it's possible, like from the perspective of the client, it may well be that A and B got created or modified from the last fetch.
Yeah, in principle, it could have happened, correct? That was a recurring modification. We do know, because like we were, sort of looked from the top, and we know that basically C read the file after A and B modified it. But the server can pretend as if it actually happened concurrently. And in a second, we'll see that if we stick the fetches in the log, the server cannot pretend to do that.
Okay, but even if the server pretends that, is that even a problem? Does it break anything? Because the client can.
This is the example where it shows that it breaks something, correct? Like step one, C fetches off.py. The server gave it one, as part of the fetch, it gave it the prefix. And so the client constructed the file system, executed the operation, returned off.py to the application and installed the software on the machine, just to make it very crisp. So now the first reading off the PY, that operation is done, right? Finished, already executed, and has installed the old version of the PY on the machine. Then the client, fetches bank.py. Now the server actually, the client or the application wants to read bank.py. So the client fetches the log from the server, or asks the server, please give me the log. The server this time around gives the whole log, and not just the prefix.
Yeah,
The
but
client, builds up the whole file system and returns bank.py to the application.
in wouldn't this happen in an incorrect implementation of the client? Because if the client finds that, receives the log, and it sees an additional modification on A, if the client knows that its logic depends on A and B being in sync, it would also fetch A again.
Yeah. Okay, so there's a great question. C doesn't know, correct, that is C, okay. In this particular scenario, we're trying to establish whether actually, C can determine whether actually the modification happened concurrently or in the past, before it read it. We want to be in the case that it actually happened in the past because it actually really happened in the past. But what this server does, it just pretends that the modification actually happened concurrently with actually C's operations. And C doesn't really have any way to detect that, other than it knew, maybe that there should have been a modification for A and B together. But that only could have known if there was sort of communication between C and A and B. And in a second, let's talk about that in a second. But if C had not talked to A and B, then it could have gotten, it could have ended up in this scenario where it installed the old version of off.py and the new version of bank.py. And we'll see in a second, if we stick the fetches in, then this problem just cannot happen. Somebody asked if we timestamp everything, then we could detect things. Hold that thought for a second. Okay, let's look at the with fetch scenario, right? So and see what actually happens in that case. So client fetches, wants the fetcher of off.py. Oops, what happened now? Hold on a sec. I think something went wrong. I presume nobody can see my screen yet. Nobody can see my screen.
It's black for some
Yeah,
reason.
it's coming back. Hold on a second. I definitely feel today there's a Byzantine component to 824. Okay, I need to stop sharing the screen for a second. All right, we're back, hopefully. Okay. Let's see this. Okay. So back to this example where now the fetches are in the log. C fetches the off.py. So let me continue with. Well, then let me save this for just. Fetches off.py. The server, sends the prefix. So basically, it sends these modifications correct? Because the server can just return whatever it likes. Then, in this new plan, correct, where the fetches actually are being logged, then C constructs the file system using A and B, and then returns that, of course, auth.py to the client or to the application, and then it adds a fetch to the log and uploads that log to the server, and then it does a fetch of bank.py, and the server in our previous example, so in the first example it said just the prefix. So here's the prefix. Now because now the client sends the whole thing, right? So it sends the whole log, and but if the modifications are not in it, and we'll have to send the whole log. Well, to send the whole log, it must include the fetch from C, correct? And so, and if it doesn't, send the fetch from C, it actually sees that the C is not there, the read operation, and basically the client will reject the log because actually its own fetch operation is actually not in it. So it's not possible for the server to pretend, that to send the log later on, because actually the new log should have included that fetch operation that was in it, and the C or the server cannot splice that fetch operation into here to make it consistent with what actually happened before, because that would be detected because the modifications on the records of A and B are not wouldn't check out. Okay, so basically what this really does is to sort of step back, is that you can think about this attack that the server sort of pretends that the modification to A and B happened concurrently with the C reading it, even though we know that actually is not the case, and by sticking the fetches in it, that attack cannot happen.
I have two questions.
Yeah.
Maybe first, just if you could define for consistency and the fetch modify consistency, and then the second is, in this example, so what exactly is stopping the server from placing the fetch in the right place of the log?
Because remember, every log entry covers all its preceding entries.
Okay, so if for example,
the server could not splice that fetch after the prefix before the modifications of A and D.
So let's say it only wants to send the modification of A. It knows the hash of the modification of A and everything preceding it, and then it could insert the fetch to C there because it knows that
it could say
the hash of that. And
yeah,
so
but then it could
hashes
send
that.
Yeah, but then it couldn't send the modification to B, because the modification for B, is directly after A, and so A must, and so it can't splice it between A and B either.
I see. Okay.
Sorry, and what was the problem with having it where it is in the picture?
Well, where it is and now in the picture is perfect. It's fine, correct? And in fact, this basically suggests, that the fetch of C actually included the modification of A and B. Like the blue was the real log, and we have the fetch into C in it, and everything is going to be perfect.
So just to clarify the definition for consistency.
Yeah. Hold on a second, because this is the topic of this slide. I haven't talked about the definition of for consistency yet. I'm going to do that right now. Okay. So we're going to talk about for consistency. So what we've seen so far is that the server cannot really manipulate the log. It can only sort of send prefixes, or it can hide parts. It can send a prefix back to the client, but it can't really modify the log. So it just basically has an opportunity to sort of show different logs to different clients, and that is basically what for consistency is. And so it cannot provide, so the kind of the server cannot provide the type of consistencies that we've seen so far in the past, namely like linearizability and external consistency and things like that. That's just not possible. But it can provide this, what the paper calls or introduces is fork consistency. And let me abstract a little bit away and to explain what that is. So let's say we have client A, we have the server S, and it has a log. Let's say I'm just going to abstract everything away. It has entries A, B, C, and D, and E. And A, whatever, maybe appended that entry to the log, and that's basically it. And maybe we have another client B, and what the server can do is sort of give the other client a completely different view of the world by basically have another copy of the log, or its own copy, or give it a different copy of the log. For example, maybe that log contains the record A, but then every operation that B does goes into this log, B1, B2, maybe even some operations from other clients that also get this view end up in this log, but they're not actually shown to A. A basically, A may actually also add more entries to the log, like maybe it adds B, C, D, and E, and those are not actually shown to B. And so these two logs to the world view of A, looks completely consistent because it's unaware of any of B's changes. And to B, this log looks completely consistent because it's not really aware of any A's changes, right? Because in this model of the world, the only sort of shared communication place that is there is the server. That is sort of the the thing that shows what actually is the state of the system. And one way you can think about it is in terms that we've talked about before. This is sort of like a split brain. Basically, A gets the C1 view of the world, cooked up by a log that's consistent with A's view, and B, gets another view of the world. And basically, the server keeps them sort of carefully separate, and therefore can pretend that A is looking one, sees the left side of its brain, and B sees actually the right side of S's brain. Okay, does that make sense? So that's sort of what basically they're saying is we can't really do better than fork consistency because it's always possible for the server to basically make a copy of the log, and then from then on present different views to these clients. Now, S could not merge the two logs again, correct? These logs have to be separate, for A and B, because it's impossible for S to sort of take the logs, let them grow for a while, and then basically splice these two logs together again, because because these entries protect all these preceding entries, these entries protect all the preceding entries of those, and so you can't put them back together. And because the signatures wouldn't check out, because the signatures always cover the current entry plus all the preceding entries. And so the only thing that basically the server can do is basically split the world, fork the world into two different logs. So they might have a common log in the beginning, then the server forks them, and now the A and B basically operate in different worlds. And that's sort of what the definition of fork consistency, and that is basically the best this particular file system, this particular system can do if there's the only communication actually happens between S. Notice actually, by the way, that sort of fork consistency is good enough for our particular application Zookeeper, correct? Because either the server shows the old version, without A and B, or the server shows to S, the modification with A and B. Okay, so what do you do? It seems like maybe this is actually a problem. How do you detect forks, and how could you? So how do you detect forks? Well, there's sort of two schemes that the sort of paper mentions. One is out-of-band communication. And this is pretty straightforward. If A and B ever talk to each other, and for example ask each other, hey, what is your last entry in the log? And they get different answers, they know that they have been forked. Because either they they could have different answers, but like at least one should be the prefix of the other. And if that's not the case, then they know that they're actually they have been forked. So that's one possible scenario that they discuss in the paper. To basically share, the clients periodically exchange the last log entries, the last entry in their log. Another solution, which actually was mentioned in the chat, is introduce what they call sort of a trusted machine that is a timestamp box. And basically, like every few seconds, it actually adds a timestamp to the log, and every client knows that basically maybe it's a file in the file system that just contains the current time. Every time the timestamp box, every couple of seconds, the timestamp box updates that file. The clients read that file, and they know there should be a new modification like every couple of seconds. And that basically, that fork that contains the timestamp box is sort of the fork that the clients that the server actually has to present to the clients. Okay. So that's the two things that actually the paper discusses. And what's sort of interesting, and we'll see on Tuesday, is that this whole fork detection and fork resolution approach is sort of a key problem basically in Bitcoin, right? And we when we were talking Tuesday about Bitcoin, we see a way basically to settle on a fork. So even if the file system or the server, the Byzantine servers actually have created a forks, Bitcoin basically has a way of just deciding, well, we're going to reach a consensus on like which fork we're going to actually proceed with. And so we'll leave that up until Tuesday. But here's sort of a connection, between SUNDR and actually Bitcoin. Any questions about this? Okay. Okay, now I want to talk very quickly, because I have sort of 3 minutes left, about the other. So I think the key thing out of the paper is the log conceptual view of the world. Of course, it's impractical, as I mentioned earlier, and so SUNDR actually has a proposal for how to do it better, even though like other systems like Bitcoin actually do maintain the whole log. And so what does SUNDR do to things better? Instead of actually maintaining a log, that's actually has snapshots, similar to sort of the snapshots that we've seen before, in Raft, where we construct a part of the world based on the log. We take a snapshot, and that actually forms the current state. And in fact, really what the SUNDR does, it actually doesn't really literally take snapshots. It really maintains a snapshot view of the file system and does it per user. So one way to think about it is that the file system is sort of sharded by user. Every user has its own view snapshot of the world. And there's a little bit of a protocol to make sure that these different snapshots from the different users are actually consistent. And let me talk a little bit about how actually SUNDR actually makes that snapshot. Basically, in SUNDR, basically there's something that's called the user I handle. And the user I handle basically uniquely identifies a snapshot in the file system. And basically is a cryptographic hash of the I table, which includes all the I nodes in the system. And for every I node, there's a hash of the I node, which basically covers all the data, all the blocks belonging to that particular I node. And so, for example, when say A modifies auth.py, it might write one block. The client recomputes the hash of this block, updates the entry here, updates the entry here, updates the entry here, and that's basically a new handle that describes basically that captures the complete file system. And I'm going to ignore the group and the directory I'll block for for a second. So this basically gives you a complete checkpoint or a snapshot of user 2's view of the file system. Now, and then to deal with this issue of how to get sort of consistency across users, they have this notion of version vectors. And what a version vector is pretty straightforward. Every version vector has an I handle, like A's I handle is in it after it modified, say, off.py. And then for every user in the system, the version vector has a counter for the number of modifications that were made by that user. So if A made this update to off.py, that counter is set to 1. B didn't make any modifications. C didn't make any modifications. They're all 0, and this whole thing is signed. And so when B makes this modification, so here's the version vector for B. This is A's version vector. So if B makes a version, it creates a new handle that includes, of course, all the modifications or represent all the modifications. And in its version handle, it actually, or in its version vector, it includes how many operations it read by its user. So it will record the fact that, for example, that it actually saw A's modification. It updates B to B1 and C to B0, and basically signs to this whole thing. And now C, when C actually does an operation, wants to read off.py and fetch and bank.py, it basically downloads all the version vectors from every user. And so in this case, it will get the version vectors for A and B, takes the latest one, which in this case is B, because actually it includes all the operations of A in it. And that's basically the represented version of the file system. And from that version, it reads off.py and bank.py. And note, that basically it's impossible for the server to basically present bank.py and not off.py, because it cannot, the only two sort of version vectors it can return is this version vector or this version vector. The version vector A doesn't include actually the changes of bank.py. If C actually does get the versions of bank.py, it must actually have the versions, the modifications that A has made, because the version vectors are constructed in that way. And so that's basically the way for using version vectors to detect that S doesn't drop changes as the same way that the logging system has done. Okay, so that's the essence of the version vector plan. So in summary, okay, Byzantine participants, are sort of a problem that you have to handle in decentralized systems, because there's no single institution that sort of can be the source of trust. And we've seen this notion of signed logs as a very powerful tool to deal with malicious servers. And as I said on Tuesday, we're going to continue this discussion, and you'll see how the signed logs are used in Bitcoin, in particular, like how fork consistency, or how the fact that forks are sort of being created are being resolved in the case of Bitcoin. All right, so that was it for as an introduction to sort of decentralized systems, and I hope the paper is a little bit more understandable than maybe when before you start reading it earlier this week or today. Okay, see you on Tuesday. And of course, if there's questions, please feel free to hang around. If you need to go somewhere else, absolutely go somewhere else.
I have a question about the data structure that they used, the B+ tree or whatever. Like, what's the difference between that and like a Merkle DAG, for example?
Oh, it is a Merkle data structure. I think the person who's sort of credited with this idea is Merkle. And that's why often it's called the Merkle data tree.
So this is the same thing?
Yeah.
Okay.
Yeah, SUNDR basically uses a Merkle tree.
Sorry, when you are verifying the signatures, does it mean you have to like basically as you go, if you're 100 entries into the log, you have to compute, I don't know, the hash of all the 100 entries concatenated and then compute? And
Yeah, so you need to keep a running hash. Okay, let's go back to verify. Yes, that's it. Okay, so here's probably a good place to talk about it. So here, so let's say take the last entry, correct? The last entry will have a hash of the preceding entries. And so everything, from the whatever records, let's say this is 0, 1, and 2, 0, 1, and 2. Or basically has the hash of the previous entry, number 2. In it, and that needs to be checked. And the way that is being checked is in principle, if you start really from the beginning of the world, you would have to compute the hash of record 0. You find out what the hash is, and double check that corresponds to the entry that's in here and that the signature is valid, et cetera, et cetera. Now, of course, in the real system, you can remember most of the log and just double check that, like whatever and start from there.
okay, so it's inefficient. Okay.
Yeah, if you have to replay from the beginning of time, you basically have to really validate the whole log from the beginning of time.
Thank you. That makes sense.
Yeah, you'll see this in the Bitcoin paper, right?
So are the hashes like almost like a Merkle chain? Like
Yes.
Okay.
Yeah, same idea.
So are the is the leaf in the sort of tree or chain like an entire file or like blocks of a file?
This is a block, one block. So this is 4,596 bytes. And all the other hashes don't change, correct? So it's actually not that inefficient.
Yeah, because if you only change part of the file, it only rehashes that part.
You just have to rehash that one, and then you have to recompute the hash of the tree.
Yeah.
All the way to the user's I handle. And the paper talks about there's sort of a couple of optimizations to make this more efficient, but hashing is actually generally not that expensive. The signing is the more expensive operation.
I had a question about version vectors.
Yeah.
So we use version vectors to make sure that the system can't return like an old state.
Yes.
So why can't the system just return the old state and the old version vector if it keeps like a second copy?
Yeah, it can fork. Right.
So we only have fork consistency then with the
version vectors only for consistency either.
Okay.
SUNDR for consistency, no more.
Got it.
So for consistency, you need the timestamp?
Before consistency, I mean the server can fork the log at any particular point in time and present a consistent view of the what they can merge logs back together. So really, this picture that the server can actually construct different views of the world and split the world in multiple worlds, but it can't merge the worlds back together undetectedly.
So the best we can do is for consistency, which allows for forking, but we can detect forking.
Yeah.
So if we detect forking, can we then get something stronger than for consistency?
Well, well, we can settle on a fork. We're going to have forks, but we can try to settle, like pick one fork as the one to go forward with.
Okay. But SUNDR doesn't have a way to do that.
Nope.
Okay.
SUNDR doesn't have to do that.
I mean, SUNDR does propose some methods, no?
methods to detect, and basically, what basically proposes like you use the timestamp box to
Yeah.
Use that one.
Right. Thanks.
You're welcome.
The timestamp box is just a server that appends entries and
Yeah, and is trusted. So it's not under control of the adversary.
Thank you.
can I also ask one final question about the Debian example you said in the beginning? Can you say again what happened there?
Yeah, sure. So basically, this is the source repo, the development machines for Debian Linux in 2003. An attacker compromised, broke into those machines and modified files. And this is the distribution that has then been sort of handed off, which, if you run Debian Linux, you're anybody who got like the Debian Linux after the attack, got maybe a compromised Debian Linux. And so as soon as they discovered this, they didn't do any further development and no more further distributions. They sorted out, like, went to backups, started comparing files from backups with the files that they have, and basically double checked that all the changes that were in the repo are actually really legit.
Okay.
And roll back any changes that are not legit.
Wait, that is pretty bad.
Yeah, it's pretty bad. And it just occasionally happens. This is a real problem. It's a real problem in practice.
Thank you so much. That was a very interesting lecture. Thank you.
You're welcome.
Thank you.